The next part is kinetics. I know recently there are a lot of questions related to how to use the rate determining step, how to use the steady state approximation, how to use the pre-equilibrium approximation. So I believe all of you guys have a good understanding about this part. But I want to extend this question a little bit. So if you still remember, this is the first time for the steady state approximation to be assessed in the local exam, right? Previously, it was assessed in the national. So this is the trend. More and more national level questions are in the local exam. And the national exam are getting slightly harder. And obviously, the top 20 students are getting stronger. And then the performance of the United States team in the IJO is getting better, right? In the recent 2 years, I think the US team got the second place. We don't want to derive this equation anymore. If I didn't remember wrong, the answer is still D? Can you guys check for me? I kind of forgot. I remember it's D. This is not 2019, it's 2017. 2019 have a different one. It's D, okay? So let's confirm the answer is D. And then I have some further extended question. So obviously, can you tell me what is the overall reaction here based on our accumulation in organic chemistry? Did you realize this is the SN1? Is the unimolecular substitution, nucleophilic substitution, right? You see, the first step, we make a carbocation intermediate. The second step, the intermediate is attacked by a nucleophile, right? So it makes sense, it's SN1. Realize this, right? So my second question is, which step in the above reaction is slow? How do you think, guys? Oh, we got different results. You guys have different opinion about this. If you recall the content we discussed yesterday, for SN1, did you remember the energy profile? Right? The first step, you need to break down a bond. You need to break down a carbon-bromine bond, right? So this is why the first step will have a higher activation energy. And the second step is just a cation met with an anion and then make a compound. So it should be has a much lower, right? Now this makes sense to you? Okay, so my next question is, for us to apply the steady state approximation, what kind of criteria we should have? Why we can assume the concentration of the intermediate will not change with time? Yeah, I know the intermediate is almost zero, right? The concentration, why is almost zero? Yes, you guys are all correct. So the production of the intermediate is slow. K1 is small. And then the consumption of the intermediate is fast. K-1 and K2 are both large. So which means the concentration of the intermediate will be remain in a very low value because once it is produced, it is immediately consumed, right? So this is why we can make this assumption, and it's also reasonable for an SN1 reaction, right? Makes sense, right? So my next question is, does the answer follow the SN1 kinetics rate law? It should be like this, right? It looks like it doesn't fit, but actually it's reasonable. Because first, if you compare these two values, which one is greater? K2 and K minus 1 probably are comparable, right? Because they are both making the products. But in the beginning, can we say the BR minus is much smaller than the N3 minus, right? Because the N3 minus is the reactants and the BR minus is the products. So in the initial stage, we can say the BR minus is almost zero, and then we definitely can ignore this part, and then you will cancel this value, and then you got this equation, right? So which means probably if we talk about the rate, and this is the concentration of the, or let's say the time, maybe this is not right, never mind. Okay, so some further points about this question. I like this question very much because I always try to think about a little bit more about the question. So we already summarized the criteria to apply the SSA. Let's summarize it again. So which means we need to have a fast reaction after the rate determining step. Maybe this is not a good summary. Let's do the summary later. I will have the summary. I have a challenge practice problem for you to try. So here we want to talk about this part. So the steady state method can only be used if the first step of the reaction is much than the second one, slower or faster. Right? Makes sense, right? It should be slower. And how about the pre-equilibrium approximation? It requires the first step to be fast equilibrium. Why? Why it should be like this? If the first step is a fast equilibrium and the second step is slow, and then we can make the assumption the second step will not affect the concentration of the products in the first step. And then we can say, okay, the reactants and the products are in a kind of equilibrium state. Make sense? I have something I want to show you, but I don't know whether I can make it or not. Let me have a try, guys. Give me 1 second. How can I get this link? I probably showed this to my student, but I think this is really a good simulation. So I want to show to you guys, but it requires the Java. But right now, most of the browsers do not support Java anymore, especially Apple. Apple hates Java. Give me 1 second. Seems like I made it. There is something weird. Okay, maybe you guys can try it, by yourself after class. Just a little bit reminder. First, you may need to have a IE, so which means Safari doesn't work. Or you can download a kind of old year Firefox. So the most updated Firefox doesn't work because the most updated Firefox does not support. Maybe I can try it. Just give me 1 minute. Firefox, let's say 39. I will download the old version of the Firefox because every time when I download it, it's automatically updated. So okay, the internet is not too slow, so I think I can make it in 1 minute. Yeah, now this software, they are very evil. They always want to give you, their most outdated version. So let's say you guys can take a 1 minute break. I'm working on this. It's almost done. Just wait, a few more seconds. Okay, it is coming. Okay, where's my Zoom? Share. Okay, can you see my screen? No problem, right? Okay, finally it is here. So, so you see 3 lines. Let me see. So the red line is the concentration of A changing with time. The blue line is the C. The green line is B, right? So this is kind of the Okay, this is when we apply the steady state approximation. Because right now, if we unclick it, these 3 lines are the exact concentration. This is the steady state approximation. So as we remember, you cannot see the blue. The blue one is here. Do you mean you are colorblinded? Okay, anyway, so if we need to apply the steady state approximation, what is our requirement? Steady state approximation. So which step should be slow? The first step should be slow, right? So now say we make the K1 smaller. Uh-oh, too small. And then make this larger. So you will see the steady state approximation will give you a really good fit, right? And then if you apply the pre-equilibrium approximation at this moment, obviously it doesn't work. And we need to have a fast equilibrium for the first direction and has a low second step. And then you will see they fit pretty well. So I think, this kind of simulation give you some good idea about what is the criteria for you to apply the SSA and the PEA. Okay. Let's go back. So for kinetics, I think, you know, there is no really hard questions. I probably want to, you know, skip this part. Let me see. Let me see. Maybe we can have a look at this question. 30. You guys can have a look. Yeah, 30 is a tough one. So actually, I was confused for the first time when I work on this question. I'm confused by what? I don't know what is the first step reaction, what is the second step reaction. So actually, the first step is B changed into C. And then the second step is A plus C changed into D. So obviously, the first step has a slightly larger, you know, activation energy. So we can say the first step is a little bit slow. The second step is a little bit faster, although it might not be so obvious. So for the two options, the reaction display a second order kinetics. Can we say that? Why we cannot say this? Because if we say the first step is the rate determining step, so it seems like A is not involved in the rate determining step, right? So some of you ask about if A is a third party in the first step. I don't think so, because otherwise A will be the catalyst, right? So I think we should compare A is not involved in the first reaction. But why we still want to put A here is because you want to compare the free energy of the overall A plus B, A plus C with D. Otherwise, it doesn't make any sense if you accidentally, you know, first is B, and the second one is A plus C. You cannot make this kind of comparison. So this is why we want to put the A here, but it's very confusing, right? I kind of worked for a while and then I realized, okay, the A is not involved in the first step. And then the reaction obviously has only one intermediate, which is C, right? So the answer of the question is clear. So I have a few questions here. Is the first step reversible? It's kind of almost reversible, right? Because you see, the two activation energy, the forward one and the reverse one, are pretty much the same, right? So I would like to say the first step is kind of reversible. So what kind of approximation you should use if you want to derive the equation, the rate law? Right? We should apply the SSA, right? I think. So my next question is, in which case the reaction will display a second order kinetics? Yeah, we need to make the second step like this, right? Make the second step slow. And then for the first step, we can use the pre-equilibrium approximation. And then you will see the rate equals to K2 times A times C. And the C's concentration will be expressed by this. And then you substitute the C into the first one. You get the second order reaction. You are right. The second step needs to be slower than the first step. Do you know what is the Kf and Kb here? Kf means the forward reaction rate constant. Kb means the backward reaction constant, rate constant, right? So this is called pre-equilibrium approximation, right? So I think, by analyzing those few questions, we have a better understanding about what are the criteria to use different approximations. Okay, so I think, the 2019 USNCO local is not very hard, so I will skip it. Next one is the Arrhenius equation. I think you guys are very familiar with this equation, and actually it's almost have the same style as the Van 't Hoff equation. The only difference is this is the lowercase of k because it's the rate constant, and there is the uppercase of k, is the equilibrium constant. And here is the EA, there is the delta HR, right, standard. So they are slightly different. And another difference is delta HR can be positive, can be negative. How about EA? EA is always positive, right? So this is why when temperature increase, the K will increase, right? And similarly, we'll have a figure like this. The y-axis is a long K, and K is the constant, the rate constant, and x-axis is 1 over T. So based on the slope, you can get the activation energy. So actually, this is how Arrhenius measure the activation energy for a lot of reactions. So at that time, we don't have Excel. We even don't have calculator. So I believe Arrhenius is a very smart guy because he kind of get different temperature, got different rate, and then he tried to figure out what is the relationship of these two, right? Because if you just plot these two, probably it will give you something like this, which is similar to a logarithm. No, it's not like this because it's 1 over T. So it should be kind of very complicated, right? Arrhenius is Arrhenius. Oh, here is another thing, is kind of how the temperature affects the rate constant. So the temperature will be more effective for a reaction with a high activation energy, or will be more effective for a reaction with a low activation energy. Right? This is a question assessed in 2018 local. Right? So the answer of the question is D, right? The rate that varies more with temperature. So if we need to analyze it, you need to see something from here. So let's say the temperature change is the same. So let's say you change from T1 into T2. So you will see the delta long K is greater for a high activation energy reaction and is smaller for a low activation energy reaction, right? So you guys can do some mathematics by yourself by using the Arrhenius equation. You will get the same conclusion because this picture actually is based on the Arrhenius equation, right? Let's have a look at this. So this is a exothermic reaction, so which means the energy profile is like this, which means the EA of the forward reaction is smaller than the EA of the backward reaction, right? So obviously, if you increase the temperature, both the forward and reverse reaction will increase, right? but the reverse one with a higher activation energy will increase more. So this is why how the equilibrium will shift. The equilibrium will shift to the right side or the left side. It will shift to the left side, right? Because the backward reaction rate increase more. Now, is this consistent with the Le Chatelet's principle? Yes, I want you guys to have something, try to connect all of those stuff, right? Connect the kinetics with the thermodynamics, with the equilibrium, okay? So, this is also a very interesting question, right? I believe this question has a very, very low correct percentage. If you still remember this question. It seems like the answer should be B. And I believe most of the students choose B for the first time. But actually, the answer is not B. Okay, how many of you, did the experiment of the fading of CV plus in AP chemistry or in any other class? Let me ask you. Let's say A is you did the experiment, B is you didn't, okay? A is yes, B is no. Wow, this is very unfortunate. A lot of you didn't do this experiment before. Someone choose C. What do you mean? Okay. Okay. I just want to get a kind of brief information about how many of you did the experiment. Actually, not so many. So I want to briefly introduce the experiment. So the general idea of the experiment, CV plus is a dye which is purple. And then we add some hydroxide, it changes into a product which is colorless. So we apply the spectrophotometer to monitor the absorption. Based on the Beer's law, we know absorption equals to epsilon BC, so which means the absorption is proportional to the concentration of the C plus. So which means we can monitor the C plus changing with time, right? So obviously it will decrease with time when you add the hydroxide. So the lab wants you to measure the order for both, the order of the CV plus, the order of the hydroxide. So how can you work on the order of the CV plus? First, you will compare two different concentrations of CV plus, right? But you will keep the hydroxide constant. But how can you make sure the hydroxide is kept in constant? Because when the reaction is going on, the hydroxide will also change with time, right? Use buffer. Buffer doesn't work because we need to use the hydroxide. So which means the key point for the lab design is keep excess of hydroxide, which means although the CV plus will consume some small amount of hydroxide, but still the hydroxide is much more excess, so which means its concentration is approximately unchanged in the process, right? This is called pseudo. How to spell pseudo? P-S-E-U-D-O. Pseudo first order, right? Okay, now let me ask you a question. So if the concentration of the hydroxide is the same as the CV plus. So now, since the CV plus is first order, so you will get CV plus, the ln CV plus VST is linear. How about the hydroxide? Because it's a 1-to-1 reaction, right? So which means the ln hydroxide is also a linear relationship when you plot the logarithm with T. Make sense? Right? So let's assume actually the order for hydroxide is 0. If the order for hydroxide is 0, you will still get this, right? When the concentrations are the same. This is exactly the situation here because the initial concentration of A and B are equal. So even the order of hydroxide is not 1, is 0, you will also get this equation because when 1 mole of CV plus is consumed, 1 mole of hydroxide is also consumed. Did I make it clear? So the answer is D. The order of A cannot be determined based on the information. Okay, let me try to explain it again. So let's think about a situation. Both of these two are 1 mole per liter in the initial case. And then we know the order for CV plus is 1. The order for hydroxide is 0, right? And then since the order for the CV plus is 1, so the ln CV plus over T or VST is linear, right? Is it linear? You agree with this part, right? And then we know when 1 mole of hydroxide, when one mole CV plus is consumed, 1 mole of hydroxide is also consumed. So if you plot the logarithm hydroxide versus T, you also get a linear relationship. Do you agree with this conclusion? And then, obviously, your conclusion is different from the real case, right? Because the real case is not first order, it's 0 order. I think Michael has a great conclusion, right? So this is a very interesting question, and I actually like it. So you will see, this is a standard AP experiment. And obviously, I believe most of you took the AP chemistry, but most of you seemed like didn't, do the lab, right? So this is the problem. A lot of AP chemistry classes, do not do the experiment. So I think this is the right direction for USNCO, right? We accumulate this kind of knowledge or skill or understanding based on hands-on experiments. Okay, this is a question from 2019 local. So you will see it's a similar reaction, not a reaction, a similar question. 50 to 60, 60 to 70 is also a math problem to apply the Arrhenius equation. So I think we don't need to discuss too much about this.